Hello, everybody. Welcome to this new webinar in our Innovation Hub series from CTS. This is the fourth one of the series and last for this fall installment. And I'll just recap a little bit. We've well, if you had the chance to attend the other webinars, we've talked about different things, composites, lead-free piezoceramics, and the last webinar in date was about D33 measurement. And today the focus will be textured piezoceramics, and more precisely the relationship between processing and properties. My name is Charles. I'm the product manager for Piezo at CTS. And today I'm just here to introduce our first speaker, Dr. Mark Fenton from Penn State University. Mark, the floor is yours.
Wonderful. So thank you, everybody, for joining this morning, this afternoon, this evening, wherever you happen to be. As Charles said, I'm Mark Fenton from the Penn State Applied Research Laboratory. I'll be presenting today on some work that we've done looking at the relationships between the properties of textured ceramics and the degree to which they are textured. Before I move on, I just want to acknowledge all of my team members here at Penn State. Certainly a team effort on this particular effort, and beyond this effort, the team at CTS as well. So today we'll talk about textured ceramic processing just from a brief overview point of view, talk about why we expect to see changes with texture fraction, and then dive into the impact of changes in texture fraction of the ceramic on the fundamental matrix coefficients of the material, which is really where you go in terms of understanding how the material may perform in a given piezoelectric device, and then talk a little bit about where we're going for future work. So I think everyone is probably quite familiar with the traditional ceramic processing when it comes to piezo materials. The block diagram on this slide just provides a very high level overview of the traditional ceramic process geared towards dry pressing a ceramic component or a piezo ceramic component. The textured ceramic process takes a bit of a detour out of this normal process flow, in the sense that we're going to change the way that we dry the material and the way that we build it into a green body for sintering and downstream processing. So for the textured ceramic process, in the wet stage, after the material is milled and before it's dried, we add large template particles to that slurry, and then step through. In our case, today we're going to talk about tape casting as the process for drying that slurry into a form that can be used for building a green body. And we'll talk on the next slide about why we do that. But in general, what we are using are well-known, long-used ceramic processing methods. While they may not be necessarily widely used in the piezo ceramics industry, they are widely used in other ceramic processing industries, so that we're not having to develop new processing tools or techniques in order to create textured piezo ceramics. Why we use tape casting in our particular case is because it allows us to align these template particles that we're adding in the slurry stage. So in very simple terms, when you tape cast, the doctor blade in the tape casting system provides a shear force on the slurry, which forces these asymmetric templates to align. So they tend to have a 10-to-1 or 20-to-1 aspect ratio in terms of their X and Y dimensions versus their thickness. And this results in the shear force creating a torque on the template, which drives it to align parallel to the flow direction of the slurry through the doctor blade. Then we take advantage of the fact that during sintering and grain growth processes, the larger particles in the matrix tend to consume the smaller particles in the matrix. So these intentionally added large particles that are crystallographically aligned with respect to one another drive the formation of a textured microstructure by consuming the random grains that surround them. And so you can see in the photos at the bottom of the slide, on the left, these large barium titanate templates embedded in a very fine-grained random ceramic matrix. The middle picture showing the initial stages of sintering and densification, where we've got this dense fine-grained matrix very closely compacted around our template particle. And then finally, a microstructure image showing how these templates expand and create essentially a brick wall microstructure with textured alignment from top to bottom in the slide. So in this particular case, the crystallographic alignment is along the 001 crystallographic direction, top to bottom in that right-hand image. And what we really want to know is, can we get from the image on the left to the image on the right in a very repeatable manner? And can it be done over large areas and at thicknesses up to, say, 1 centimeter? The idea being here that this isn't just a laboratory curiosity. We want to understand, what does it take to be able to process this material on an industrial scale, and can you do it in a way that's repeatable and economically viable? Why we worry about this, there was some modeling work that was done at Penn State several years ago by Lon Chen's group, primarily, looking at what happens to a simple performance metric like the D33 coefficient as you change from a random ceramic here on their axis, denoted by the 1.0 value on the x-axis, to nearly single crystal or fully single crystal, denoted by an R equals 0. You can see that as the material textures, you drive that D coefficient upward pretty dramatically. And they modeled a couple of different types of materials here, one being perfect material, some with isolated pores, and some with barium titanate templates present. This is all binary PMN-PT ceramic, but the trend is the one that concerns us from a manufacturing point of view. If we're trying to reach very high displacement coefficients, we need to have a very high texture fraction. And the steepness of this curve suggests that perhaps process control could be a bit of an issue here. If you can't repeatably achieve the texture fraction you're after, you may find yourself in a situation where you're processing material with quite a degree of variability, which is obviously not desirable from a manufacturing point of view. So we'll go through sort of some more examples of this using real world data, just to give you an idea of, one, how the material properties vary as a function of texture fraction in the real world, and how you can potentially use that to actually tune the performance characteristics of the material for a given application. So in this case, what we're looking at is a manganese-doped PMN-PZT ceramic, the matrix powder here being supplied by CTS in Albuquerque. And what we're looking at are the D33 coefficient across a collection of small Tompilts rings. And you can see some variability in displacement coefficient amongst different groups of tiles that were used to make these rings. So each one of the 3 large groupings that you see in this diagram were different trips through our sintering furnace. And so the question becomes, what role is texture fraction playing in the spread of this performance data? Within the group, probably not much, but from group to group, are we controlling the repeatability of our process, particularly our sintering process, in such a way that we're achieving a repeatable outcome. So for this work, we used traditional IEEE sample geometries for characterization. These were all, again, manganese-doped PMN-PZT textured ceramics, which is a general purpose transmit and receive material, thinking about it from an acoustic point of view. All of the samples were cut from 75 millimeter by 35 millimeter plates that were 3 millimeters thick. And we cover quite a range of texture fractions using this same geometry. We used traditional 3-3 mode bars, 3 millimeters long with a 1 by 1 millimeter cross section, 3-1 mode bars to get the lateral coefficients, 9 millimeters long with a 1 by 3 cross section. And then we used 10 millimeter discs. And all of these measurements made at 1 kilohertz and 1 volt drive level. And everything aged more than 100 days prior to testing. And everything pulled and tested through the texture direction. So in terms of this plate, notional plate that we're looking at here, the texture direction would be through the thickness of the plate. So the first thing we looked at in order to compare it to some of the published modeling and simulation data was, what is the D33 coefficient doing as a function of texture fraction? And you see that we do essentially replicate the trend that the modeling paper predicted, that to get to very high D coefficients, we need to drive the texture fraction as close to 100% as possible. And this is using Lotkering factor as our measurement for texture fraction, which is a technique which essentially uses the peak intensity ratios from an X-ray diffraction pattern, comparing the 001 family of peaks to all of the other peaks that are present between 20 degrees 2 theta and 70 degrees 2 theta. It is a very rapid technique that is very amenable to being used as a production QC tool. It provides a fairly coarse level of texture fraction estimation, certainly not to the degree of information that you would get from a rocking curve or some other measurements, but one that's fairly simple and easy to make from the standpoint of process monitoring. So this is what we've decided to use for this particular data set. In terms of dielectric performance, you also see that the dielectric constant is a pretty strong function of texture fraction. Surprisingly, dielectric loss is not. That is really more set by the doping and the stoichiometry control of the material during sintering. So a constant dielectric loss suggests that we are actually treating these in an equivalent fashion in the sintering process, despite the fact that each one has arrived at a different value of texture fraction. Of course, we're also interested in this material from a receive point of view. So looking at the G33 coefficient is one example for something like a hydrophone application. In this case, we see very little change in G coefficient as a function of texture fraction. So from a hydrophone point of view, there is perhaps a little bit less concern with process variability. However, there have been some recent results, both published and here internally at Penn State, that suggests that for hydrophone applications, you may not actually want to drive the material to 100% texture. In cases where it's really the hydrostatic coefficients that you're more concerned about, where you're looking at the interplay between the say the 3.3 coefficient and the 3.1 coefficient, there's actually a maximum in that hydrostatic coefficient at lower texture fractions. And so again, this comes back to the idea that understanding process control for the texturing process is really critical in order to arrive at a consistent output from this new material. Compliance coefficients likewise change with texture fraction as the material begins to trend more towards something that looks like a single crystal. The compliance coefficients also trend towards more single crystal-like, and the compliance coefficient gets higher. The material gets mechanically softer. This would allow you perhaps to, within a range of texture fractions, tune the stiffness of the material in addition to some of the other coefficients. If you're trying to achieve, say, a particular resonant frequency within a given package size. Likewise, coupling coefficient also changes significantly with texture fraction. As the stiffness coefficient increases and the D coefficients increase, we do see a significant rise in coupling as well. In these particular cases, if bandwidth of a device is really critical, then driving towards the highest possible texture fraction is obviously going to be critical. Thinking about this at a higher level, I've already sort of alluded to the idea that perhaps you can use process control here as a way to tune the material. This particular plot shows a more or less linear relationship between the D coefficient and the stiffness, driven by the algebra that we're all kind of familiar with here. Interesting that it does kind of extrapolate all the way back to some of the harder PZT materials. So that it does begin to beg the question, maybe there's some wider space to play in here in terms of giving yourselves another way to tune material performance by tuning texture fraction. Ongoing work for us here at Penn State, we're continuing to explore and try to understand and tailor the high field characteristics of the PMN-PZT phase space. Certainly for very high drive acoustic applications, that's of interest. We are actively exploring the ability to tailor density and material compliance without sacrificing D coefficients or coupling coefficients. Certainly the impact of processing is top of mind for us, especially for our relationship with CTS and trying to work this partnership for technology transfer, wanting to understand the impact of additive manufacturing as an alternative to tape casting, particularly for certain part geometries or for more complex geometric builds. Understanding the impact of water-based processing versus solvent-based processing is really critical. We do see some significant differences there. New compositions, of course, are certainly of interest from a basic research point of view. From our perspective, we're actively working new compositions for receive-only applications, looking at what we can do in other composition space to maximize coupling coefficient for really broadband device applications. And again, looking at these really high duty cycle, high power applications where low self-heating is really a desirable outcome as well. One of the things that we're just beginning to look at in the area of energy harvesting is the impact of grain size on the performance of textured PMN-PZT. As you noted in some of the initial diagrams of microstructures, the grain size of the textured material can be 4 to 5 times, if not more, the grain size of a traditional PZT material. And there are a lot of open questions regarding the impact of that grain size on, say, fracture strength of the material or the impact of cyclic fatigue as a function of grain size as well. And we're actively pursuing those questions as well. Temperature effects and hydrostatic and uniaxial pressure effects are also two particular areas that are keeping us busy. From a transducer design point of view, there are certainly gaps in the data that we have on PMN-PZT and other materials to help a designer understand, say, in a Tom Piltz device, what is the impact of, say, uniaxial preload on the performance of that device? How much do we impact capacitance or D coefficients by putting the device under a compressive load? And then understanding non-linearities in terms of temperature effects is also a critical thing for us. So with that, I will stop sharing my screen and hand this over to Dr. Jerry Stranford, Senior Engineering Manager at CTS in Albuquerque.
Thank you, Mark.
Just while Jerry is setting up, I want to mention that everybody's welcome to ask questions. There is a Q&A tool, and there's actually a couple of questions there. I think the general idea is that we can take the questions at the end, but if we have just a minute while Jerry's setting up to maybe answer one, that would maybe save us some time.
Sure,
I see there's
sure.
a question about what types of template materials are used, and if it's only barium titanate.
So it is not only barium titanate. There have been a range of template materials explored, primarily perovskite type materials. So barium titanate, strontium titanate, lead titanate. We have, where possible, tried to match the template particle as closely to the matrix that's being textured as possible. In the case of the PMN-PZT, I would say we're not as well matched as we would like to be, but there's not yet technology available to let us grow a template particle that's, I would say, compositionally closely matched to that particular material.
Yeah. So there are limitations in terms of which materials can be processed for texturing.
There are, and I would say it's not well understood, the interaction between the template particle and the matrix as far as when you can drive texture and when you can't. So we have primarily focused on materials that we know single crystals can be processed from, because we know they have a tendency to want to texture when single crystals are easily made from them.
All right. Then I suggest we go through Jerry's presentation. That might also answer some of the questions there, and then come back to the questions at the end, if that's okay for everybody.
All right. Thank you, Charles and Mark. And as I get started here, I'd like to acknowledge our ongoing collaboration with Mark Fanton and his team at Penn State. As he mentioned, we're looking at trying to industrialize the process. And what I'm going to talk about today is at least one of the challenges that we've faced as we try to scale this up, particularly what happens as we go to thicker cross sections during the sintering process. I think Mark alluded to that a little bit in his presentation. You know, as Mark mentioned, we're working with this manganese-doped PMN-PZT. So the composition is on this pseudo-cubic tetragonal MPB, morphotrophic phase boundary, in the phase diagram. And we do produce this in 100-kilogram batches. So we have successfully scaled up the base composition to what we would consider an industrial scale, a typical batch size that we would work with here at CTS. Incidentally, by way of background, CTS has multiple sites around the world. I'm located in our Albuquerque, New Mexico facility. Okay. Mark already described the texturing, so this is largely reiterating it, but successful texturing requires a small matrix particle size, aligned templates. Right now, the predominant way of achieving that is tape casting, as Mark mentioned. And then there has to be template lattice dimensions similar to the matrix. During the actual sintering process, we need to get the density of the matrix high prior to the start of that grain growth, which Mark talked about. And the way that's achieved is by liquid phase formation within the material during sintering. So that liquid phase will promote densification at low temperatures. And then later on in the cycle, as the grains are growing, it also acts as the mechanism to transport material from the small grains to the interface growing around the templates. So it's a solution reprecipitation process, moving the material and causing the grains to grow around the templates. So in our process, we form that liquid phase by, first of all, we do add some excess PBO to the base formulation. And then also during the sintering process, we have to create a high lead oxide vapor pressure atmosphere during sintering. Over here on the right, I just show a couple of micrographs, so similar to what Mark was showing. We've got, we see the template and the fine grain matrix. This is just a green fracture surface here. And then following sintering, we see a relatively dense microstructure. These short, dark lines here are the templates, and the grains have grown around them. The darker areas are porosity in the material. And one thing I'll point out throughout my presentation, there's numerous micrographs. They're all taken in backscatter electron mode. So it's reflecting the average atomic weight of various areas. So the lighter the area, the higher the atomic weight, meaning more lead oxide present. Okay, a little bit more information on the texturing process. In the lower left here, we see the matrix powder. This is after it's been milled to approximately 0.7 micrometers average particle size. And then we have the templates here, barium titanate templates. I'll say typically on the order of 15 micrometers square by 1 to 2 micrometers thick. And on the right, we've got looking at the process partway through. So this is at 1,000 degrees Celsius. We can see that we've densified the fine grain matrix, and we've started to get the grain growth around the template here. So when you look at it, as stated earlier, that we really needed to get a high density prior to the grain growth, and that liquid phase is really helping us with this because I didn't step back, but by 900 Celsius, we see that the the matrix itself is well densified. So that wouldn't be possible without the presence of the liquid phase. The bottom micrograph is going further, 1100 degrees C. This wouldn't necessarily be our endpoint. We do go to higher temperatures, longer times during our sintering cycle. But you can see you've got a large amount of grain growth around the templates, and the fine grain microstructure is fully, is basically consumed, growing larger grains. There are a few areas I want to point out here that, because it'll be a topic further on, is there is some lighter areas here, which are residual liquid phase that of course is solidified after we cool down, but it's a lead oxide rich phase that's present in the microstructure. And I believe that's one of the things that's affecting our reproducibility and making the challenges that we experience as we try to go to thicker cross sections. Okay. This is an X-ray diffraction pattern of an as-centered surface for a 1.25 millimeter thick sample. About 3 years ago, when we first started working with Mark's team, just to get a feel for how we could get good texturing, we had our facility in Denmark tape cast some material to it for us and do a layup that was roughly 1.25 millimeters thick. So we did a lot of initial work on this, and after much trial and error and thought, we had pretty good success. You see the X-ray diffraction pattern here is dominated by the 001, 002, and then the little one over here is 003 peaks from, and showing that we have a high degree of texturing. The lot carrying F factor here, we've got 0.998, so we've actually got very high level of texturing, and we achieved a D33 on this particular sample of 950. But to show that there is some variation, I threw in this box plot. The average is about 950, but we actually, on various samples, all from basically the same tape that we were working with, the same layup we were working with, centered at different times, ranged from about 750 up to 1075. So this was very encouraging. And then we went to a thicker sample, in this case, 8 millimeters thick. And you see, we do still get high level of texturing. Once again, this is at the surface. We're seeing 0.991, so very high level of texturing. But on the other hand, our D33 now is down around 574, and our dielectric constant here is 1460, considerably lower than the 2000 we saw for the thinner sample. Okay. So then we took a look at some microstructures here, and when we look at the 1.25 versus the 8 millimeter thick, a couple of things that I see on these is that the thinner sample seems to be more porous, whereas the thicker sample may be higher density, but a lot more of this residual lead-rich phase in the microstructure after sintering. And we took a look at various thicknesses over time. All the data points here represent the same tape cast stack up of materials. So the basic raw materials going in are the same, the tape cast is the same. The only real difference here is our sintering. And we found that we got a pretty linear relationship, and it's inversely, the finding that the D33 is inversely proportional to the thickness of the material. So that led us to say, what's going on as we go through the thickness of the material? So we took the one of those 8 millimeter pieces that we'd been sintering, and we, for first machining to get the surfaces flat and parallel, it was ground to 6 millimeters thick. You can see the XY dimensions here are 20 by 40 millimeters. We then sliced this into 0.66 millimeter thick wafers. So we were able to get 5 full thickness wafers out of this 6 millimeter part. I've indicated the 001 direction here. So each of these wafers does get pulled through, electroded and pulled through the thickness. And, prior to doing that, though, we did run the X-ray diffraction pattern on each of the parts in wafers, and we find that as we go through this stack of 5 wafers, we've got high F factor, good alignment again, all above 0.99. But a little bit closer look at this 002 peak here in the smaller figure, we see that slice 3-1, which would be close to one of the surfaces, well, first of all, let me back up. When we take a close look at this, we see there's actually a little bit of tetragonality here. We're seeing 2 peaks. So the one by my cursor here, the one on the right would be the 200 peak, and then over here would be the 002. So zooming in on these, we see that the one near the surface, the intensity of this 002 is very similar to the 200. But then as we get beneath the surface, this 002 peak declines in intensity, suggesting that as we move away from the surface, we're probably becoming more tetragonal in structure. To refresh your memory, if this was a purely tetragonal material, the 002 peak would be 50% the intensity of the 200. So we do seem to be having a phase shift as we go deeper into the material. One of the things I want to point out here is that because of the grinding of the surfaces, these wafer slices probably aren't symmetric out of the sample. So I'm speculating here, but I believe that the 3-1 slice is closer to the surface than, for example, the 3-5 slice. So there's a slight asymmetry here that I wasn't able to get worked out. After electroding and pulling, we took a look at the properties of the material, and we see that that slice 3-1, which has the highest D3, or excuse me, it shows the least amount of tetragonality. I'll say has the highest dielectric constant and the highest D33 coefficient. But then as we look at the other 4 slices, we see they've declined a little bit. Here we're going from a dielectric constant of about 1550 down to around 1400, maybe a little bit lower, but fairly consistent between the other 4 slices. Same trend with the D33. We're going from about a 610 here down to around a 570 D33 coefficient. And similarly, when we take a look at the hysteresis loops for these materials, we see some slight differences. You know, one of the things now this was a different set of slices. So the slice 1.5 here is the one that had the highest D33 coefficient. As I looked at several different parts and it was always consistent. On one side, I had one slice that was very high in D33, and then the rest came down. But that one seems to be, the hysteresis loop is shifted a little bit, and suggests that there's a little bit of an internal bias field present in that material. Whereas the other ones, I just showed one for clarity's sake, but slices 1 through 4 in this case were all similar. As you see over here, where I plotted P sub R and E sub C, they were very similar, and it was just that last piece that showed the anomalies. So looking at these slices, I looked at fracture surfaces here, and the top one is for a lower D33 coefficient material, whereas the bottom one is the higher D33 coefficient. And similar to the micrographs that I showed earlier, when we have the higher D33, we tend to see more of that porosity showing up, and the lower D33, less porosity, but more of that residual PBO rich phase. So that brings me down to this is a work in process. So what I'm about to show here is just my current thoughts on what I think may be going on. And you know, if we take a look here at the thin cross-section material, you know, as I stated up front, creating that very PBO-rich atmosphere during sintering was one of the crucial steps that we identified several years ago to achieving the high level of texturing. Early in the cycle, some of that PBO vapor is going into the material and condensing it. We have confirmed it. We actually, at certain points during the cycle, our parts do show a mass gain, which then is given up later on in the cycle. So very early in the cycle, that lead oxide penetrates in and is able to assist with the densification as well as the texturing. Then late in the cycle, much of that PBO evaporates out. And on the thin surface or thin cross-section pieces, I believe that you know, almost all of it's coming out. Whereas in contrast, when we go to the thick cross-section, once again, early in the cycle, we probably get the PBO vapor penetrating deep into this cycle, but and condensing to help form that liquid phase. But as we get towards the later portion of the cycle, only the surfaces are losing some of that excess material, leaving us with a microstructure that is probably more porous near the surfaces, and I'll say generally we see less of that residual PB-rich phase in cross sections after the fact. But in the middle, we still have that liquid phase showing, which is the dark phase you see in these, and it pretty much is probably getting entrapped in there, and it's not easy for that to diffuse out or find its way out. So you know, couple of things that are probably going on here. I mentioned about the trapped liquid phase. In the presence of that liquid phase, it would just naturally bring the properties down a little bit because it's not going to perform as high as the base composition. But also due to some of the interactions with the liquid phase and what gets dissolved into that liquid phase and what gets precipitated out, we're probably having some subtle shifts in the ratio of the major cations that are sitting on the B site. So some of the things we're taking a look at, trying to see if we can mitigate this and get higher properties with the thicker cross sections, is we're looking at optimizing our sintering profile and the lead oxide vapor content in the atmosphere during sintering. And then the other one that I've just started, so it's very early on, but looking at a slight compositional adjustment that might take into account you know, a shift in these ratios in our actual grains occurring because of the presence of the liquid phase. My thought being that perhaps if I get closer to whatever the composition is migrating to, I can get away with a little bit less liquid phase and make the process more reproducible. Yeah, I thought it was interesting in Mark's presentation. He points the steepness of that curve on the texturing and the potential challenges that create from a process control standpoint. And yeah, working in an industrial environment, yeah, I look at that and say, yeah, that does make a headache for what we would call design for manufacturability. So definitely one of the things we would like to have better control over and be able to routinely hit a particular endpoint. Okay. So that concludes my presentation today, and I can stop sharing my screen and Charles can bring the questions to the forefront.
All right. Well, thanks, Jerry. I think we still have a few questions focusing on the templates. I can see there's a question about whether we manufacture the barium titanate templates in-house.
Okay. No, we purchased those templates from a company in Turkey.
Yeah, in terms of not barium titanate, those are things that we are working on, sort of refining the manufacturing process for in our lab.
All right. There's a question, I think, Mark, you mentioned in your presentation the work you're doing focusing on the water-based versus organic-based binder. There's a question whether you could elaborate a little bit more about your experience on this topic.
Sure. So mixed metal oxides, especially ones that are mixed transition metal oxides, tend to have some amount of solubility in water. Barium titanate's kind of the classic example. There's a substantial problem in processing barium titanate in water if you don't adequately passivate the particle surface. And so the same sorts of things can happen in these lead-based ferroelectric materials, where some of the cations actually want to dissolve to an extent in water, depending on the pH of the slurry that you're using and kind of how you're managing that. The texturing process requires you to mill the material to a pretty high specific surface area. So you have a lot of surface exposed for these oxides to interact with the water that's present. And that can lead to issues during the sintering process, as those dissolved metals have to reincorporate back into the crystal structure. The other thing that happens is most of the water-based binder systems that are used for tape casting also tend to be quite sensitive to the concentration of dissolved metals in the water. So traditionally, to avoid those problems, you would go to solvent-based processing, where the oxide is essentially immune to any effect from, say, a polar solvent. So in the case of CTS, they're looking at a process that's different than ours, in the sense that they're using an organic-based process where we are using water-based. And so comparing what Jerry gets in his process to what I get in mine helps shed some light on what is driven by aqueous processing versus what is driven by solvent processing.
All right, thank you. While we're talking about processing, there is a question about 3D printing. What kind of 3D printing technology do you think will be most feasible?
So I'll give my perspective, and then Jerry can give his as well. But we are rather partial at the moment to a process originally proposed and developed by Sandia National Lab, which is sort of generically termed robocasting, where you create a shear thinning paste that can be used to build up materials layer by layer. And the advantage of that particular process is that it's essentially tape casting on a small scale. So you're shearing a paste through a very fine nozzle as a way to create shear for your template particles. There are, of course, other processes, primarily ones that say use a recoater blade. So the lithographic type processes are particularly amenable to texturing as well, although it's not something that we've pursued directly.
Yeah, I mean, overall, I agree with Mark. The work we've done internally so far has all been the robo-casting or direct ink writing type process. I know we have discussed some the lithographic processes, but do not have any direct experience with that. But I agree that that's a possibility as well. But ultimately, the challenge is how can you get the material to flow out and get the templates properly aligned.
Yeah, one of the issues with the lithographic processing at the moment is that the wavelength of light used for the lithographic exposure tends to be absorbed pretty heavily by highly doped PZT compositions. So if you're trying to print a hard PZT, say a PZT-8 or a PZT-4, they tend not to lithographically print very well because the ceramic particles absorb all of your optical energy. There has been more success printing the softer PZT formulations that are not doped as heavily.
All right. There is a question about cost. Are these textured parts more expensive than the regular ones? Well, I think I can answer yes to that. But it's probably a question about how much, right? Maybe I could say just a few words. Obviously, there is more processing involved with the tape casting, or whether it's tape casting or 3D printing. And there's also an impact of the geometry of the part. So currently, if we use tape casting, then we manufacture rectangular blocks. And if we have to deliver a circular part, then obviously there's a lot of material waste. So this also has an impact on the cost. I think some of the work we've done on the cost aspect was to compare a regular PZT, textured, and a single crystal material. Because with the textured ceramics, what we're trying to achieve is to have performance that is somewhere in between regular ceramics and single crystals. And I think in terms of the cost, that's also a little bit where we are actually. So we are a certain factor, depending on the geometry again, let's say 2 to 5 times more expensive with the textured material compared to a pressed ceramic. Whereas with the single crystal, we are looking at something more like factor 10, 20 or more. So this is pretty much where we are in terms of the cost. But as you heard from the discussion, we're also working on like 3D printing to optimize this cost. All right. I don't know if that answered the question, or if any of our guests have something to add to that.
Yeah. No, I think you summarized it pretty well, Charles. Kind of the other thing inherent with the say the PMN system is we're starting at a higher raw material cost base just because of the niobium in there.
Yeah, that's true.
Yeah, I mean, at the end of the day, you'd really like to get back to being able to texture your base PZT formulations. Right now, I don't think we understand well enough the process to be able to do that. Jerry showed a ternary phase diagram at the beginning of his talk. As you move down that phase boundary towards just the PZT leg of that phase diagram, you lose the ability to texture the material. And I don't think we understand exactly why that happens. There's I think a lot of fundamental understanding that needs to be plugged in to drive us towards being able to texture some of these more long-standing compositions.
Yep. All right. I think we have time for a few more questions. Let me just read the last one. Textured variation could be due to non-texturing effect of some templates.
Yeah, certainly. In the template material, you we'll get particles that don't align because they're too small or because they're the wrong shape.
Yeah, I'd say there's also some possibility of dissolution of the template into the matrix. I'll say that's something we obviously see sometimes, not so much other times. But I've also found if we stop the process, the sintering process at low temperatures and look at the phase, our composition's actually shifted a little bit more tetragonal. I assume that's probably because of some of the barium titanate dissolving in and moving, at least the titanium is moving us towards that lead titanate portion of the phase diagram.
Yeah, I think, and the other thing we're trying to come to grips with in terms of template alignment is that in both direct ink writing and tape casting, the shear field is sort of two-dimensional in nature, but you're trying to align a three-dimensional particle. And so you're not always necessarily you're not applying a torque in all of the directions on a particle to achieve perfect alignment.
All right. Questions from Oliver. Could we shake the grains with ultrasound to facilitate the liquid phase removal?
It's an interesting question. I can't speak to the liquid phase removal, but it is a technique that we're exploring to be able to understand when the liquid phase appears and how it evolves over process time. So we're looking at designing an acoustic system that would allow us to watch the modulus of the ceramic as you heat it and as you hold it at temperature and allow that liquid phase to form and then dissipate. So as a characterization tool, you can certainly do that. As a process tool, I wouldn't dare speak to that.
I assume it would be tricky to do that above 1,000 degrees. Yeah. High temperature ultrasound generators. All right. Question from Eli: why G coefficients is not affected as much as D coefficient with texturing?
Physics. So yeah. it's really driven by the ratio between the D coefficient and the dielectric constant. And since both are increasing, the G doesn't really change much.
All right. Okay, I suppose we still have a couple of questions there. Why is it necessary to age the samples for 100 days before the measurement?
So for us, that's just following some standard PZT industry practices. We wanted to make sure that the samples were not still continuing to change in properties with respect to time. The traditional PZT materials do show a typical decrease in properties over time on a logarithmic scale. And going out to 100 days, make sure that the materials are essentially stable. Jerry might be able to speak more than I can to aging effects on the textured materials.
Yeah, it's early on, particularly with those thin samples, when we were looking at the textured materials, one of the interesting things we found was when we got the high texturing fraction, consequently got the high D33 coefficients. Initially, the part D33, for example, and dielectric constant would be increasing, which is kind of puzzling to those of us that have discussed it. We don't understand that, but eventually at some point it does start to come back down. And so going out to approximately that 100-day age seems to get you away from whatever that unique phenomena is. We speculate that is probably driven by some sort of stress that's created initially due to the texturing process and then the pulling process on a material. Interestingly, you do not see that when the D33 when the material starts with a D33 coefficient lower. What I'll say is in that case, let's say something around 600, the aging rate's pretty low, but I have not had the opportunity to really quantify that yet, but there would still be some aging going on. You definitely don't want to be looking at these parts and taking the data to the bank based on measurements at even 1 day, that they're still kind of settling down after the pulling process at that point.
well, one more question. Do you have any data about stress and temperature stability of texture ceramics?
From my end, very little at the moment. I think temperature stability, because these are relaxer ferroelectrics, is a critical thing to look at. With most of them having a phase transition temperature somewhere well below the Curie temperature, it is something to be aware of compared to traditional PZT materials.
Yes, we did actually at CTS perform some initial temperature tests, and we see we measured the K31 coefficient on a IEEE sample, and we can see the results are relatively stable up to about 100 degrees, and then we start to hit a transition temperature. We see a decrease. Although the material is still usable, we do see the decrease from 100 degrees up to, I think, around 180. And we tested, but actually it's a reversible process. So we use some parts up to 150 degrees and cool them down, and we still get the same coupling coefficient when back at room temperature. So there is some decrease in performance above 100 degrees, but still relatively high coupling coefficients, and it's a reversible process. On the stress front, I don't have any results to share at the moment, but it is something well, it's on our list to look into, definitely.
Yeah, we are actively pursuing that data set at the moment, understanding the impact of uniaxial stress on the material.
Yep. All right. Does texturing degrade with electric fatigue?
I think the fatigue characteristics of the material are also an open question.
Yeah, I agree with that. I think that's a unknown and will need to be investigated.
All right. Well, I think we covered both the questions and the time, I believe. So I hope everybody, all the attendees, have received the answers they were looking for. Otherwise, well, don't hesitate to contact us by email. I think you will get a follow-up questionnaire for the evaluation of this webinar. And once again, I'd like to thank our speakers, Mark Fenton and Jerry Strandford. Thank you very much.
Thank you, Charles. Appreciate it.
Thank you.
All right. Thanks, everybody. Have a good day.
Thanks, you too.
Bye.